In the depths of our universe lurks a terror beyond comprehension, a massive cosmic void stretching 330 million light-years across. The Decay void, often called the Great Nothing, is an empty region of space so vast it defies our understanding of physics. While it should contain thousands of galaxies, this colossal sphere of darkness holds only a handful, as if something has cleared away the very fabric of the cosmos itself. To comprehend its scale, if our entire Milky Way galaxy were the size of a grain of sand, the Decay void could hold millions of such grains. Yet it stands virtually empty, a dark desert in the cosmic ocean that challenges everything we thought we knew about how our universe formed and operates. In this video, we will explore this and other terrifying anomalies that exist in the depths of space. These aren't theories or science fiction. These are real phenomena that continue to baffle scientists and challenge our understanding of reality itself. Before we dive into these cosmic horrors, don't forget to like and subscribe to Space Mysteries for more mind-bending content about our universe. Prepare yourself as we journey into the most frightening discoveries in the history of astronomy. The discovery of the Decay void in 1981 marked the beginning of a new mystery in cosmic exploration. When astronomers first spotted this region through radio telescopes, they assumed their equipment was malfunctioning. The odds of such emptiness occurring naturally were astronomical, quite literally. What makes these cosmic voids truly terrifying isn't just their size, but their implications for our understanding of the universe. According to our standard models of cosmic evolution following the Big Bang, matter should be distributed relatively evenly throughout space. The presence of such massive empty regions suggests there are fundamental forces at work that we don't yet understand. These voids aren't truly empty. They contain a sparse web of dark matter, invisible to our instruments, but detectable through its gravitational effects on surrounding galaxies. This dark matter behaves differently within the voids, moving in patterns that contradict our current physics models. The physics behind void formation presents an even more perplexing puzzle. Current theories suggest these cosmic deserts emerged from quantum fluctuations in the earliest moments of the universe, mere fractions of a second after the Big Bang. These initial fluctuations, amplified by cosmic inflation, created regions of slightly lower density. Over billions of years, gravity worked to enhance these differences, drawing matter away from these regions and toward their boundaries. Beyond the Decay void lies an even more extensive network of cosmic emptiness. The Eridanus supervoid, spanning nearly 1 billion light-years, represents one of the largest known structures in the universe. This supervoid coincides with an unusual cold spot in the cosmic microwave background radiation, suggesting a possible connection between void formation and the fundamental properties of spacetime itself. The KBC void, discovered in 2013, presents an even more disturbing revelation. This gigantic void, approximately 2 billion light-years across, appears to encompass our entire local galactic neighborhood. The implications are staggering. Our entire Milky Way galaxy, along with its nearest neighbors, might reside within the outskirts of one of these cosmic deserts. This positioning could affect everything from our observations of distant galaxies to our calculations of universal expansion rates. The boundaries of these voids reveal another layer of cosmic complexity. These edges, known as void walls, contain some of the most dense concentrations of galaxies ever observed. These galactic walls form vast filaments and sheets, creating a cosmic web that spans billions of light-years. The Sloan Great Wall, stretching over 1.37 billion light-years, represents one of the most massive structures ever discovered and forms part of a void boundary. Within the voids themselves, the few galaxies that do exist display unusual characteristics. These void galaxies tend to be younger, bluer, and more actively forming stars than their counterparts in denser regions. They're also significantly more isolated, sometimes separated from their nearest neighbors by tens of millions of light-years. This isolation has led to unique evolutionary paths, creating galaxy types rarely seen in more crowded cosmic neighborhoods. The relationship between voids and dark energy presents another fascinating aspect of these cosmic deserts. Dark energy, the mysterious force driving the universe's acceleration, appears to have a stronger effect within void regions. This strengthened influence might explain why voids continue to grow faster than predicted by standard cosmological models. As the universe expands, these regions of emptiness expand even more rapidly, potentially leading to a future where cosmic voids dominate the universe's structure. Mapping these voids has revolutionized our understanding of cosmic structure. Modern surveys, using advanced techniques like weak gravitational lensing and galaxy redshift measurements, have revealed that voids aren't simply empty bubbles in space. They form complex, interconnected networks that follow specific patterns. These patterns, when analyzed mathematically, suggest an underlying order to the apparent chaos of cosmic structure. The influence of voids extends to the very fabric of space-time. Within these regions, the usual rules of gravity appear slightly altered. Light traveling through voids experiences subtle changes in its properties, creating effects that astronomers can measure. These modifications to light's behavior might offer clues about the nature of dark energy, and potentially even the existence of modified theories of gravity. Environmental conditions within voids present extreme versions of cosmic emptiness. The density of matter in these regions can be as low as 1/10 the cosmic average, creating conditions that can't be replicated anywhere else in the universe. This extreme emptiness makes voids ideal laboratories for testing fundamental physics theories and searching for exotic phenomena. The future implications of void expansion raise disturbing possibilities for cosmic evolution. As voids continue to grow and merge, they could eventually dominate the universe's structure, creating vast regions where normal matter becomes increasingly rare. This process, combined with the accelerating expansion of the universe, suggests a future where galaxies become increasingly isolated, potentially leading to a universe where most regions resemble today's voids. The most recent theoretical models attempting to explain void existence incorporate concepts from quantum mechanics and string theory. Some propose that voids might represent interfaces between different quantum fields, or even connections to other universes within a larger multiverse. While these ideas remain speculative, they demonstrate how the study of cosmic voids pushes the boundaries of theoretical physics. The timeline of void discoveries reveals a pattern of increasingly larger and more complex structures. From the initial discovery of the Boots void to the identification of void complexes spanning billions of light years, each new finding has forced us to revise our understanding of cosmic scale and structure. This progression suggests we might still be underestimating the true scale and complexity of cosmic voids. Current and future research directions focus on understanding the role of voids in cosmic evolution. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are mapping void structures with unprecedented precision, while theoretical work continues to explore the connection between voids and fundamental physics. These studies might reveal not only the origin and nature of cosmic voids, but also provide crucial insights into the largest mysteries in modern cosmology. The existence of these massive cosmic voids forces us to confront an uncomfortable truth. The universe is not just stranger than we imagine, but stranger than we can imagine. These cosmic deserts stand as testament to our limited understanding of the cosmos, reminding us that even in an age of unprecedented scientific achievement, some of the universe's greatest mysteries remain unsolved. As we continue to study these enigmatic regions, we edge closer to understanding not just their nature, but the fundamental principles that govern our universe's structure and evolution. Among all the terrifying phenomena in our universe, Magnetars stand as perhaps the most violent and destructive stellar objects ever discovered. These cosmic monsters represent nature at its most extreme, possessing magnetic fields so powerful they could strip away your blood's iron atoms from halfway across the solar system. Magnetars begin their existence as massive stars, at least 8 times more massive than our Sun. But unlike regular neutron stars formed after supernovae, Magnetars emerge with magnetic fields trillion times stronger than Earth's magnetic field. Their surface magnetic fields reach strengths of 10 to the power of 15 Gauss, strong enough to distort atomic structures and create bizarre states of matter we can barely comprehend. The physics behind these objects defies conventional understanding. Their magnetic fields are so intense that they actually warp the surrounding space-time fabric. They create conditions where quantum effects, typically only observable at atomic scales, manifest on a macroscopic level. Virtual particles spring into existence from the quantum vacuum, only to be torn apart by the overwhelming magnetic forces. The surface of a magnetar exists in a state unlike anything else in the universe. The intense magnetic field creates a strange form of atmospheric pressure, compressing the star's outer layers into a crystalline structure of iron nuclei. This magnetic atmosphere behaves according to quantum rules rather than classical physics, creating conditions that cannot be replicated in any laboratory on Earth. When magnetars undergo starquakes, severe disruptions in their crust, they release more energy in a fraction of a second than our Sun will emit in 100,000 years. These bursts can cross vast distances of space, affecting planetary systems thousands of light years away. The most powerful recorded magnetar burst, detected in 2004, briefly paralyzed our space-based instruments and partially ionized Earth's upper atmosphere, despite originating from a source 50,000 light-years away. The process that creates magnetars' magnetic fields remains one of astrophysics' greatest mysteries. The dynamo theory suggests that in the moments after a supernova, the newly formed neutron star spins incredibly rapidly, completing hundreds of rotations per second. This spinning, combined with complex fluid motions in the star's interior, amplifies the initial magnetic field to extraordinary levels through a process called the alpha-omega dynamo. The extreme conditions around magnetars create unique phenomena never seen elsewhere. The intense magnetic field causes photons, particles of light, to split into two, merge with virtual particles from quantum vacuum, and follow curved paths through space. Light itself behaves differently near these objects, displaying properties that challenge our understanding of electromagnetic radiation. Magnetars also demonstrate remarkable evolutionary patterns. Unlike other stellar objects that maintain relatively stable properties over millions of years, magnetars undergo dramatic changes over human observable timescales. Their magnetic fields decay over thousands of years, releasing enormous amounts of energy in the process. This decay manifests as various forms of radiation, from X-rays to radio waves, creating unique signatures that allow astronomers to identify and study these objects. The discovery of magnetars has forced us to revise many fundamental concepts in physics. Their existence proves that magnetic fields can reach strengths we once thought impossible. They demonstrate how matter behaves under extreme conditions, providing natural laboratories for testing theories about quantum mechanics, general relativity, and the structure of matter itself. The population statistics of magnetars present another puzzle. Current models suggest they should be relatively rare, yet we keep finding more of them. This suggests either our understanding of stellar evolution is incomplete, or magnetars represent a more common phase in the life cycle of massive stars than previously thought. The relationship between magnetars and other exotic stellar objects adds another layer of complexity to their study. Some researchers propose that magnetars might evolve into other types of neutron stars or vice versa. This evolutionary connection might explain the diverse population of highly magnetized objects we observe in our galaxy. Recent observations have revealed that magnetars might play a crucial role in generating fast radio bursts, mysterious millisecond-long radio pulses detected from various points in the universe. This connection provides new insights into both phenomena and suggests magnetars might be responsible for other unexplained cosmic events. The internal structure of magnetars remains largely theoretical, as the conditions inside these objects are too extreme to model accurately with current physics. Their cores might contain exotic states of matter, including quark matter or strange matter, forms of matter that could be stable only under the intense pressures and magnetic fields found within these stars. The effects of magnetars on their surrounding space environment extend far beyond their immediate vicinity. Their powerful magnetic fields can accelerate particles to nearly the speed of light, creating jets and winds that interact with the interstellar medium. These interactions create vast structures visible in multiple wavelengths of light, providing crucial information about both the magnetars and the space between stars. The future implications of magnetar research extend beyond astrophysics. Understanding how matter behaves in extreme magnetic fields could lead to breakthroughs in various fields, from developing new materials to advancing our understanding of fusion energy. The quantum effects observed around magnetars might also provide insights into fundamental physics problems, including the unification of quantum mechanics and gravity. The detection methods for finding magnetars continue to evolve. Advanced gravitational wave detectors might soon be able to detect the ripples in space-time caused by magnetar starquakes, while new X-ray and gamma-ray telescopes will provide unprecedented views of these objects. These observations could reveal previously unknown properties and behaviors of these cosmic monsters. The geography of magnetars in our galaxy suggests a peculiar distribution pattern. They tend to be found in regions of high star formation, particularly in the galactic plane. This distribution provides clues about their formation conditions and evolutionary history, while also raising questions about potential risks to planetary systems in these regions. The study of magnetars represents a frontier in modern astrophysics where different branches of physics intersect. These objects challenge our understanding of electromagnetism, nuclear physics, quantum mechanics, and general relativity. As we continue to observe and study them, they remind us that the universe harbors phenomena far more extreme than anything we could have imagined, pushing the boundaries of what we thought possible in nature. Deep in the darkness between stars lurks a threat more terrifying than magnetars' wandering black holes that silently drift through our galaxy. Unlike their stationary counterparts anchored at galactic centers, these nomadic monsters roam freely through space, their paths dictated only by gravity's inexorable pull. The concept of rogue black holes emerged from a disturbing realization. Not all stellar mass black holes remain in binary systems or star clusters after their formation. Some receive powerful kicks during their birth, ejecting them into interstellar space at velocities exceeding hundreds of kilometers per second. These cosmic wanderers travel alone, invisible until they betray their presence by their gravitational effects on nearby stars and gas clouds. Current estimates suggest our Milky Way could harbor between 100 million to 1 billion rogue black holes. This staggering number means that, statistically, the nearest one might be just 30 light-years from Earth, astronomically close in cosmic terms. The true terror lies in their stealth. We can't detect them until they're close enough to influence nearby objects with their gravitational pull. The formation process of these wanderers reveals the chaos inherent in stellar death. When massive stars explode as supernovae, asymmetries in the explosion can impart tremendous velocities to the resulting black hole. These natal kicks can reach speeds of up to 700 kilometers per second, fast enough to escape the gravitational bonds of star clusters and launch the black hole on a solitary journey through the galaxy. The hunting and detection of rogue black holes has become one of astronomy's greatest challenges. Unlike their active counterparts that feed on companion stars or gas clouds, isolated black holes emit no radiation. Their presence can only be inferred through gravitational microlensing, brief brightening events that occur when they pass in front of distant stars, bending and focusing the starlight with their intense gravitational fields. The behavioral patterns of these cosmic nomads follow paths influenced by the galaxy's gravitational field. Computer simulations reveal that they tend to congregate in the galactic disk and bulge, with some venturing into the galactic halo. Their trajectories through space create a three-dimensional web of gravitational influence, subtly affecting the orbits of stars and the distribution of interstellar gas. The feeding habits of rogue black holes present a particularly fascinating aspect of their existence. While they may spend millions of years traversing relatively empty space, encounters with dense gas clouds or stellar systems can trigger periods of active accretion. During these events, the black hole's immense gravitational pull captures and consumes nearby matter, briefly revealing its presence through X-ray and radio emissions. The mass spectrum of wandering black holes adds another layer of complexity to their study. While most are believed to be stellar mass black holes ranging from 3 to 100 times the mass of our Sun, some theories suggest the existence of intermediate mass rogues. These larger variants, weighing hundreds to thousands of solar masses, might represent a missing link in our understanding of black hole evolution. The potential impact of a rogue black hole passing through a solar system presents a scenario straight out of cosmic horror. Long before it arrived, its gravitational influence would begin disrupting planetary orbits. As it approached, It would distort the careful gravitational dance that keeps planets in stable orbits, potentially ejecting worlds into interstellar space or sending them spiraling into their parent star. The timescales involved in rogue black hole encounters add to their menace. Their approach would be nearly impossible to detect until they were already influencing a star system's dynamics. By then, their gravitational effects would be inevitable and irreversible. A passing black hole could spend thousands of years slowly destroying a planetary system, creating a drawn-out astronomical catastrophe. Recent research suggests rogue black holes might play a crucial role in galactic evolution. As they travel through space, they act as gravitational stirrers, influencing the distribution of stars and gas. This process could affect star formation rates and contribute to the overall structure and dynamics of galaxies. Some scientists propose that these wanderers might even help distribute heavy elements through the galaxy, as they occasionally capture and shred stars and planets. The question of rogue black hole populations in different types of galaxies presents another intriguing avenue of research. Elliptical galaxies, with their older stellar populations, might harbor more wanderers than spiral galaxies like our Milky Way. This distribution could provide clues about galaxy formation and evolution, while also suggesting which regions of the universe might harbor more of these cosmic nomads. The technology required to detect and study rogue black holes continues to advance. Future gravitational wave observatories might be able to detect the subtle ripples in spacetime caused by these objects as they pass through dense stellar regions. Advanced survey telescopes could spot more microlensing events, building a better census of the wandering black hole population. The relationship between rogue black holes and other cosmic structures reveals complex gravitational dynamics. When these wanderers pass through globular clusters or stellar nurseries, they can capture companion stars or disrupt forming solar systems. These interactions leave gravitational signatures that astronomers can study to better understand both the black holes and the environments they disrupt. The future implications of rogue black hole studies extend beyond astronomy. Understanding how these objects interact with their environment could provide insights into fundamental physics, including the behavior of gravity under extreme conditions. Their study might also help us develop better models of galactic evolution and improve our understanding of black hole formation and growth. The possibility of mergers between rogue black holes adds another dimension to their story. When two wanderers pass close enough to each other, they might form a binary system or merge directly, releasing enormous amounts of gravitational wave energy. These events could contribute to the background of gravitational waves that permeate the universe. As our understanding of these cosmic wanderers grows, so does our appreciation for the dynamic and sometimes volatile nature of our galaxy. Rogue black holes remind us that space is not just an empty void punctuated by stars and nebulae, but a realm where invisible monsters roam freely, their gravitational influence reaching across light years to shape the evolution of stars and planets. In the grand cosmic dance of galaxies, astronomers have discovered something that shouldn't exist. A mysterious collective movement of thousands of galaxy clusters flowing in the same direction through space. This phenomenon, dubbed dark flow, challenges our fundamental assumptions about the universe's structure and suggests the existence of something massive lurking beyond our observable universe. Dark flow was first detected in 2008 when scientists analyzed the motion of hundreds of galaxy clusters using data from NASA's Wilkinson Microwave Anisotropy probe. What they found defied explanation. Clusters were streaming through space at velocities approaching 1,000 kilometers per second, all moving together like a cosmic river flowing toward a specific point in the constellation Centaurus. The most unsettling aspect of dark flow lies in its scale. This isn't just a local phenomenon affecting a few nearby galaxies. It extends billions of light years across space, encompassing thousands of galaxy clusters. The coherent motion of such massive structures over such vast distances shouldn't be possible according to our current understanding of cosmology. Traditional gravitational theories fail to explain this massive movement. According to the standard model of cosmology, the distribution of matter in the observable universe should be roughly uniform on large scales. with no single structure massive enough to create such a powerful gravitational pull. Yet something is clearly exerting an enormous influence on these galaxy clusters. The implications of dark flow reach far beyond simple celestial mechanics. If this phenomenon is indeed caused by gravitational attraction, the source must lie outside our observable universe, in regions of space-time we can never directly detect. This raises the possibility that our visible universe might be just a small bubble in a much larger cosmic structure. Mathematical models attempting to explain dark flow have led to increasingly exotic theories. One proposal suggests that our universe might have collided with another universe shortly after the Big Bang, creating a gravitational wake that continues to influence galaxy motions today. Another theory proposes the existence of massive structures that were pushed outside our observable universe during the period of cosmic inflation. The variation in dark flow's strength across different regions of space presents another puzzle. The effect appears stronger in some directions than others, creating a pattern that doesn't match any known large-scale structures in the universe. This asymmetry suggests either unknown physics at work or the presence of multiple gravitational sources beyond our cosmic horizon. Recent observations have revealed that dark flow might interact with other mysterious cosmic phenomena. There appears to be a correlation between the direction of dark flow and certain anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang. These correlations hint at a deeper connection between dark flow and the fundamental structure of space-time. The timing aspect of dark flow adds another layer of complexity to its study. The movement appears to have been consistent over billions of years, suggesting whatever causes it has remained stable since the early universe. This temporal consistency challenges explanations based on temporary or changing gravitational sources. The energy required to move such massive structures at these velocities is staggering. Calculations show that the gravitational source responsible for dark flow must have a mass many times greater than everything in our observable universe combined. This energy scale approaches levels typically associated with the earliest moments of the Big Bang. The distribution of velocities within the dark flow reveals subtle patterns that might provide clues about its origin. Galaxy clusters closer to the flow's apparent source move faster than those farther away, creating a velocity gradient across space. This gradient contains information about the nature and location of whatever is causing this cosmic migration. The relationship between dark flow and cosmic voids presents interesting possibilities. Some theories suggest that the flow might preferentially affect galaxies and clusters near large void regions, where the fabric of space-time might be more susceptible to external gravitational influences. This connection could provide new insights into both phenomena. The implications for our understanding of universal structure are profound. If dark flow is indeed caused by something beyond our observable universe, it would provide the first tangible evidence that our cosmic horizon doesn't represent a fundamental limit to reality. Our observable universe might be just one region in a much larger multiverse. The detection methods used to study dark flow continue to evolve. Advanced techniques like the kinetic Sunyaev-Zeldovich effect allow astronomers to measure the motion of galaxy clusters with unprecedented precision. These observations help refine our understanding of the flow's direction, strength, and extent. The future of dark flow research might lie in gravitational wave astronomy. If the source of the flow is massive enough, it might produce gravitational waves that could be detected by future observatories. These waves could provide direct information about whatever lurks beyond our cosmic horizon. In the grand theater of cosmic catastrophes, nothing rivals the raw, destructive power of gamma-ray bursts, or GRBs. These events represent the most energetic explosions known to science, releasing more energy in seconds than our sun will emit during its entire 10 billion-year lifetime. The discovery of gamma-ray bursts occurred by accident during the Cold War. In the 1960s, American military satellites designed to detect nuclear tests instead picked up mysterious bursts of gamma radiation from space. It took decades to confirm these bursts originated from distant galaxies, making them even more terrifying. They were powerful enough to be detected across billions of light years. The energy released during a gamma-ray burst defies human comprehension. In just a few seconds, a single burst can outshine all other sources of gamma rays in the observable universe combined. The energy released is equivalent to converting the entire mass of Jupiter into pure radiation and focusing it into a narrow beam that cuts through space like a cosmic blowtorch. These cosmic death rays come in two distinct varieties, each representing a different type of stellar catastrophe. Short gamma-ray bursts, lasting less than 2 seconds, arise from the violent collision of neutron stars. These collisions create gravitational waves that ripple through space-time, while simultaneously unleashing a devastating burst of radiation. Long gamma-ray bursts, lasting several seconds to minutes, mark the death of hypergiant stars in an event called a hypernova. Unlike regular supernova, hypernovae concentrate their explosive force into narrow jets that blast outward at 99.999% the speed of light. When one of these jets points towards Earth, we detect it as a gamma-ray burst. The immediate environment around a gamma-ray burst experiences conditions that exist nowhere else in the universe. The intense radiation creates pairs of matter and antimatter from pure energy, while magnetic fields twist and contort with strengths approaching those found in magnetars. The temperature at the core of the explosion briefly exceeds 10 trillion degrees Celsius, thousands of times hotter than the center of a supernova. The aftermath of a gamma-ray burst reshapes its galactic neighborhood. The initial burst sterilizes space for thousands of light years in every direction, stripping away the atmospheres of any planets in its path and bombarding their surfaces with lethal radiation. The explosion triggers waves of star formation in nearby gas clouds, while simultaneously destroying existing stellar nurseries. The threat these events pose to life in the universe cannot be overstated. A gamma-ray burst within 6,000 light-years of Earth, pointing in our direction, would trigger a mass extinction event. The gamma rays would destroy our ozone layer, exposing the surface to deadly ultraviolet radiation from the sun. The resultant chemical changes in the atmosphere would likely trigger rapid global cooling. Historical evidence suggests Earth may have already experienced a distant gamma-ray burst. The Ordovician extinction, which occurred 450 million years ago and killed 85% of marine species, shows patterns consistent with the effects of a gamma-ray burst. Evidence includes a rapid depletion of the ozone layer and global cooling, exactly what we would expect from a distant burst. The frequency of gamma-ray bursts reveals both reassuring and troubling statistics. In the observable universe, astronomers detect about 1 burst per day. However, because the radiation is concentrated into narrow beams, we only see a small fraction of the total number of bursts. The actual rate might be hundreds of times higher. Research into the precursor events leading to gamma-ray bursts has identified several high-risk scenarios. Binary neutron star systems spiraling toward collision provide advance warning through gravitational waves. However, predicting when a hypergiant star might undergo core collapse remains beyond our current capabilities. The distribution of gamma-ray bursts throughout cosmic history shows a disturbing pattern. They were more common in the early universe, when stars contained fewer heavy elements. However, certain regions of modern galaxies still contain the conditions necessary to produce these events, particularly in areas of intense star formation. The physics driving gamma-ray bursts pushes our understanding of nature to its limits. The jets of radiation are so tightly focused that they actually punch holes in space-time, creating regions where normal physics breaks down. The extreme conditions provide natural laboratories for testing theories about quantum gravity and the unification of fundamental forces. The role of gamma-ray bursts in cosmic evolution extends beyond their destructive effects. The heavy elements forged and scattered by these explosions seed the cosmos with materials necessary for planet formation and life itself. In a cosmic irony, these harbingers of death also help create the conditions necessary for new life to emerge. Technological advances in detection systems continue to improve our understanding of these events. Space-based observatories can now detect and locate bursts with unprecedented speed and precision, allowing ground-based telescopes to study their afterglows. This rapid response capability has revealed new details about the explosion mechanics and their effects on surrounding space. The search for gamma-ray burst precursors has become a crucial area of research. Identifying stars likely to produce these events could provide vital warning time for potentially affected regions of space. However, the complexity of stellar evolution makes accurate prediction extremely challenging. The interaction between gamma-ray bursts and the intergalactic medium reveals the true scale of their influence. The radiation from these events can ionize vast regions of space, creating bubbles of hot plasma that persist for millions of years. These ionized regions affect the formation and evolution of subsequent generations of stars and galaxies. As we continue to study these cosmic catastrophes, each new discovery underscores their role as both destroyers and creators in the cosmic cycle. Gamma-ray bursts remind us that in the universe, creation and destruction are intimately linked, and that some of the most violent events in nature also contribute to the conditions necessary for life itself. Among all cosmic threats, none is more final than quantum vacuum decay. Unlike other astronomical catastrophes that destroy stars or galaxies, vacuum decay could unravel the very fabric of space-time itself, transforming the entire universe into an alien realm with completely different physical laws, a process that would propagate at the speed of light with no possible warning or escape. The concept of vacuum decay emerges from one of quantum field theory's most disturbing possibilities. Our universe might exist in a false vacuum state. Just as water can exist in a supercooled liquid state below its freezing point, space-time itself might exist in a similarly unstable state. One quantum fluctuation in the wrong place could trigger a phase transition that would revolutionize physics as we know it. The mathematics behind vacuum decay reveals a universe more precarious than we ever imagined. Quantum mechanics tells us that empty space isn't truly empty. It seethes with virtual particles popping in and out of existence. These quantum fluctuations constantly test the stability of our vacuum state. If they discover a lower energy state is possible, a bubble of true vacuum could form. This bubble of true vacuum would expand outward at the speed of light, consuming everything in its path. Inside the bubble, the laws of physics would be radically different. The fundamental forces, gravity, electromagnetism, and the nuclear forces would have different strengths. The masses of elementary particles would change. Chemical bonds might become impossible. Matter as we know it would cease to exist. The terrifying aspect of vacuum decay lies in its absolute nature. Unlike other cosmic disasters that we might theoretically survive or escape, vacuum decay offers no refuge. The boundary of the expanding bubble moves at the speed of light, making it impossible to outrun or even detect before it reaches us. The first sign of vacuum decay would also be the last thing any observer would experience. Research into the stability of our vacuum state has produced conflicting results. Some calculations suggest we live in a metastable state that could decay at any moment. Others indicate our vacuum might be stable enough to last far longer than the current age of the universe. The uncertainty in these calculations stems from our incomplete knowledge of particle physics at extremely high energies. The role of the Higgs field in vacuum stability adds another layer of complexity. The mass of the Higgs boson, discovered in 2012, plays a crucial role in determining our vacuum's stability. Current measurements place the universe in an uncomfortably precarious position, neither clearly stable nor clearly unstable, but somewhere in between. The cosmic implications of vacuum stability extend beyond our observable universe. If vacuum decay occurs somewhere in the cosmos, the bubble of true vacuum would eventually reach us. However, due to the universe's expansion, some regions might remain forever out of reach, creating patches of space where the old laws of physics survive. High-energy events in the universe might increase the risk of vacuum decay. Particularly energetic cosmic ray collisions, the interiors of black holes, or even certain types of phase transitions in the early universe could potentially trigger the process. Each of these events creates conditions where quantum fluctuations become more likely to find a lower energy vacuum state. The possibility that vacuum decay has already occurred somewhere in the universe leads to an intriguing anthropic argument. If vacuum decay bubbles expand at the speed of light, we can only exist in regions that haven't yet been reached by such a bubble. This might explain why we observe our particular set of physical constants. They represent one of the few combinations stable enough to allow observers to evolve. The search for experimental evidence of vacuum stability continues in particle accelerators worldwide. While we can't directly recreate the energies needed to test vacuum stability, we can probe the properties of the Higgs field and other particles that influence vacuum energy. These experiments help refine our understanding of how stable or unstable our universe might be. The connection between vacuum decay and cosmic inflation raises profound questions about the universe's history. The same quantum field theory that predicts possible vacuum decay also suggests our universe underwent a period of rapid expansion in its earliest moments. This connection hints at deeper relationships between vacuum energy and the large-scale structure of space-time. Recent theoretical work has explored the possibility of multiple vacuum states with different energies. This could lead to a landscape of possible universes, each with its own physical laws. Vacuum decay might represent transitions between these states, suggesting our universe could be part of a larger multiverse undergoing constant evolution. The timescales involved in vacuum decay calculations stretch human comprehension. Even if our vacuum is metastable, its lifetime might be vastly longer than the current age of the universe. However, quantum mechanics means we can never be certain when decay might occur. It could happen at any moment with equal probability. The effects of vacuum decay on different scales present a hierarchy of destruction. At the smallest scales, fundamental particles would be transformed or cease to exist. At intermediate scales, atoms and molecules would dissolve as the forces holding them together change. At the largest scales, stars and galaxies would be converted into forms of matter governed by the new physics of the true vacuum. The philosophical implications of vacuum decay challenge our understanding of existence itself. The possibility that our universe exists in a false vacuum state raises questions about the nature of physical law and whether what we consider natural is merely a temporary configuration of a more fundamental reality. The study of vacuum decay continues to push the boundaries of theoretical physics. It requires understanding the intersection of quantum mechanics, field theory, and gravity, areas where our current theories remain incomplete. Progress in this field might lead to deeper insights about the nature of space, time, and the stability of existence itself. As we continue to explore this cosmic threat, we confront the possibility that our universe might be more fragile than we ever imagined. Quantum vacuum decay serves as a reminder that even the void of space itself might harbor hidden dangers, and that the fundamental nature of reality might be far more precarious than it appears. In the vast silence of space, our radio telescopes occasionally detect signals that defy conventional explanation. Among these mysterious transmissions, fast radio bursts, or FRBs, stand as one of modern astronomy's most perplexing phenomena. millisecond-long flashes of radio energy so powerful they can be detected from billions of light-years away. First discovered in 2007, the Lorimer burst appeared as a single intense flash of radio waves lasting just 5 milliseconds. What made this signal extraordinary wasn't just its brevity, but its power. In that fraction of a second, it released as much energy as our sun produces in 80 years. This discovery marked the beginning of a new chapter in astronomical mysteries. The energy requirements for these bursts challenge our understanding of physics. To be detectable across such vast distances, FRBs must release energy equivalent to the total output of our sun over several decades, all compressed into a few milliseconds. This energy density approaches the theoretical limits of what's physically possible in our universe. The patterns within these signals reveal even stranger properties. Some FRBs appear to be precisely structured, containing subpulses separated by exact mathematical intervals. These patterns are so precise they appear artificial, leading some scientists to consider whether they might represent technological signatures of advanced civilizations. Beyond FRBs, other unexplained radio phenomena haunt our skies. The WOW signal of 1977 remains one of the strongest candidates for potential extraterrestrial communication ever detected. Lasting 72 seconds and matching theoretical predictions for artificial signals, it has never been adequately explained or detected again despite numerous searches. The periodicity of certain radio sources presents another layer of mystery. Some signals repeat with such precise timing they were initially mistaken for lighthouses in space. The most famous, PSRB 1919+21, produces pulses every 1.3373 seconds with a precision that rivals atomic clocks. While we now know these regular signals come from pulsars, some show irregularities that challenge our models. Deep space also produces radio signatures that seem to encode complex information. The ghost signals detected by multiple observatories appear to contain structured data patterns that persist for hours or days before vanishing. These signals don't match known natural phenomena, but also resist classification as artificial transmissions. The distribution of mysterious radio sources across the sky reveals unexpected patterns. Rather than appearing randomly, some types of signals cluster in specific regions of space. This clustering suggests either unknown astronomical processes at work, or the possibility that certain regions of space possess unique properties affecting radio wave propagation. Recent discoveries have identified radio signals that appear to violate known laws of physics. Some transmissions seem to travel faster than light, though careful analysis usually reveals instrumental effects or natural explanations. However, a small percentage of these signals continue to defy conventional understanding. The interaction between these radio phenomena and other cosmic events adds another dimension to their mystery. Some signals appear synchronized with gamma-ray bursts, supernovae, or gravitational wave events, suggesting complex relationships between different forms of astronomical phenomena that our current theories struggle to explain. The technology used to detect these signals continues to advance, revealing new layers of complexity. Modern radio telescopes can detect patterns and structures within the signals that were invisible to earlier instruments. Each improvement in sensitivity seems to uncover new categories of unexplained transmissions. The search for patterns within these signals has spawned new fields of astronomical data analysis. Machine learning algorithms now sift through countless hours of radio telescope data, identifying subtle patterns that human observers might miss. These AI systems have identified several new categories of unexplained signals that don't fit any known natural or artificial source. The temporal characteristics of these signals present their own mysteries. Some appear to show evidence of time dilation consistent with originating near black holes or other regions of extreme gravity. Others display patterns that suggest they're echoes of events that occurred billions of years ago, preserved and distorted by their journey through space. The polarization of mysterious radio signals provides crucial clues about their origins. Many show polarization patterns that indicate they've traveled through intense magnetic fields or passed near massive objects that twisted and distorted their properties. These characteristics help astronomers reconstruct the signal's journeys through space. The frequency distribution of unexplained signals challenges our assumptions about natural emission mechanisms. Some transmissions appear to shift frequencies in ways that suggest intelligent design, following patterns that optimize signal strength across interstellar distances. Others show frequency characteristics that seem engineered to pierce through cosmic interference. The relationship between these signals and dark matter remains an active area of research. Some theories propose that certain unexplained radio emissions might result from dark matter interactions, or represent echoes of processes occurring in dark matter-dominated regions of space. The possibility that some of these signals represent unknown natural phenomena drives new theoretical work in astrophysics. Scientists have proposed various exotic mechanisms, from cosmic string vibrations to quantum gravity effects, attempting to explain the more bizarre characteristics of these transmissions. As our understanding of the cosmos expands, these mysterious radio signals remind us that the universe still holds secrets we're only beginning to uncover. Whether natural or artificial in origin, these enigmatic transmissions challenge our assumptions about what's possible in the cosmos and drive us to explore new frontiers in physics and astronomy. Among the most unsettling discoveries in modern physics is the theoretical existence of exotic matter states that could convert normal matter into something entirely alien. At the forefront of these cosmic threats stands strange matter, a hypothetical form of matter that could transform everything it touches into an identical state, essentially infecting the universe with a new form of matter. The concept of strange matter emerges from the physics of quarks, the fundamental particles that make up protons and neutrons. While ordinary matter contains up and down quarks, strange matter incorporates strange quarks, creating a substance that might be more stable than normal matter. If true, this suggests that all matter in our universe exists in a metastable state, vulnerable to conversion upon contact with strange matter. The process of matter conversion through strange matter interaction represents one of physics' most frightening possibilities. When strange matter encounters normal matter, it could trigger a chain reaction, converting atomic nuclei into strange matter one at a time. This process would release energy and continue indefinitely, spreading like a cosmic plague through any matter it encounters. Quark stars represent another class of matter-eating anomalies. These hypothetical objects would be denser than neutron stars, composed entirely of free quarks. The surface of a quark star would be so exotic that any normal matter falling onto it would be instantly converted into quark matter, adding to the star's mass and expanding its conversion potential. The stability conditions for these exotic states of matter reveal a precarious balance in our universe. Calculations suggest that if strange matter is stable under certain conditions, it should have converted much of the universe's matter already. The fact that we exist in a universe of normal matter either indicates strange matter is unstable, or that it's incredibly rare. The temperature and pressure conditions required for creating these matter-eating states approach the extremes found in the early universe. Certain types of stellar explosions or collisions might temporarily recreate these conditions, potentially spawning droplets of strange matter that could begin the conversion process. The detection methods for identifying matter-eating anomalies focus on their unique signatures. Strange matter would have distinct properties: extremely high density, unusual charge-to-mass ratios, and specific types of radiation emission. Astronomers search for these signatures in unusual cosmic events and exotic stellar objects. The propagation speed of matter conversion adds another layer of cosmic horror to these phenomena. While the conversion process would spread slower than the speed of light, it would be relentless and unstoppable once begun. A single droplet of strange matter could potentially convert an entire planet into exotic matter within hours. Cosmic ray observations provide both reassurance and concern regarding these threats. While we haven't detected clear evidence of strange matter in cosmic rays, some unusual events have been recorded that could potentially represent interactions with exotic matter states. These observations remain controversial and unconfirmed. The role of density in matter-eating anomalies reveals complex physics at work. As normal matter is compressed to extreme densities, quantum effects begin to dominate, potentially enabling transitions to exotic states. This suggests that the cores of the densest stars might naturally generate matter-eating states. The theoretical framework surrounding these phenomena connects to fundamental questions in particle physics. The stability of different matter states depends on the exact properties of quarks and their interactions, parameters that we're still working to understand precisely. Small changes in these values could make exotic matter states more or less likely to form. The search for matter-eating anomalies in nature has focused on several promising locations: the cores of neutron stars, the aftermath of specific types of supernovae, and regions where cosmic rays reach extreme energies, all represent potential breeding grounds for exotic matter states. The time evolution of matter-eating processes would create distinct observational signatures. As normal matter converts to exotic states, it would release energy in specific patterns. Astronomers search for these patterns in unusual stellar explosions and other cosmic events that don't fit conventional models. The relationship between matter-eating anomalies and cosmic structure formation presents intriguing possibilities. If stable exotic matter states existed in the early universe, they might have influenced how galaxies and clusters formed. Their presence or absence could help explain certain large-scale structures we observe today. The interaction between matter-eating anomalies and dark matter remains largely unexplored. Some theories suggest that dark matter might represent another form of exotic matter, possibly related to or affected by strange matter transitions. This connection could provide new approaches to understanding both phenomena. Prevention and containment of matter-eating anomalies, while currently theoretical, represent important areas of research. Understanding the conditions that promote or inhibit exotic matter formation could be crucial for future space exploration and development, particularly in extreme environments. The implications of these phenomena for the future of the universe are profound. If matter-eating states are possible and stable, they might represent an inevitable phase in cosmic evolution. The universe might naturally tend toward converting all matter into its most stable form, whatever that might be. As we continue to explore these possibilities, the study of matter-eating anomalies pushes the boundaries of our understanding of fundamental physics. These phenomena remind us that matter itself might be more mutable and unstable than we once believed, and that the basic building blocks of our universe might harbor unexpected dangers. Among all cosmic phenomena, those that distort the fabric of time itself represent perhaps the most profound challenge to our understanding of reality. These time-bending anomalies reveal that time, far from being the constant flowing river we experience on Earth, can be stretched, compressed, and even torn apart by extreme gravitational forces. The most dramatic time-bending effects occur near black holes, where space-time becomes so severely warped that time itself begins to break down. At the event horizon, time dilation becomes infinite. From an outside observer's perspective, time appears to stop completely for anything approaching this boundary. Yet for an object falling into the black hole, time continues to flow, creating a fundamental disconnect in the experience of reality. Spaghettification, the technical term for what happens when an object falls into a black hole, represents a unique form of time distortion. As something approaches a black hole, the difference in gravitational force between its front and back becomes so extreme that time flows at significantly different rates across its length. This time gradient literally stretches the object apart, atom by atom. Frame dragging, another relativistic effect, shows how rotating massive objects can actually twist time and space around themselves. Near rapidly spinning black holes or neutron stars, space-time gets dragged along like honey swirling around a spinning spoon. This effect creates regions where it becomes impossible to remain stationary relative to distant space. Everything must rotate with the warped space-time. The existence of closed time-like curves represents one of the most disturbing possibilities in Einstein's equations. These theoretical paths through space-time would allow an object to return to its own past. While most physicists believe such curves are prevented by some yet unknown physical law, their possible existence in extreme gravitational conditions continues to haunt our understanding of causality. The intersection of quantum mechanics and time-bending gravity reveals even stranger phenomena. At the quantum level, time becomes fuzzy and uncertain near massive objects. This quantum time uncertainty suggests that in regions of extreme gravity, the very concept of sequential events might break down completely. Time crystals, recently discovered quantum systems that exhibit periodic behavior in time without energy input, demonstrate that time symmetry can be broken in ways we never imagined possible. These systems, while currently only created in laboratories, might exist naturally in extreme cosmic environments, creating regions where time behaves like a crystalline structure rather than a continuous flow. The concept of gravitational time dilation extends far beyond extreme objects like black holes. Even Earth's gravity causes time to flow slightly faster at your head than at your feet. This effect becomes dramatically more pronounced near neutron stars, where time might flow thousands of times slower at the surface than in orbit. The discovery of binary neutron star systems has provided natural laboratories for studying time distortion. As these incredibly dense objects orbit each other, they create complex patterns of gravitational waves that carry information about how space and time are being warped. These observations confirm Einstein's predictions about the malleability of time with unprecedented precision. The relationship between time dilation and cosmic expansion presents another layer of temporal complexity. As the universe expands, it creates a form of time dilation that affects light traveling across cosmic distances. This cosmological time dilation means we observe distant galaxies moving in slow motion relative to our local time frame. The possibility of time machines, while seemingly fantastic, emerges naturally from Einstein's equations under certain conditions. Theoretical constructs like rotating cylinders of infinite length, also known as Tipler cylinders, or regions of negative energy density could, in principle, create paths through space-time that loop back on themselves. The fact that such solutions exist in our best physical theories suggests our understanding of time remains incomplete. The role of time-bending phenomena in cosmic censorship, the idea that nature prevents us from seeing certain extreme physical conditions, reveals fundamental limits to our ability to observe the universe. Regions where time distortion becomes infinite might be automatically hidden behind event horizons, preventing paradoxes from affecting the larger universe. Recent theoretical work suggests that time itself might emerge from more fundamental quantum processes. This would mean that the time-bending effects we observe represent distortions in an emergent phenomenon rather than a fundamental dimension of reality. This perspective might help resolve some of the paradoxes associated with extreme time dilation. The search for observational evidence of time-bending phenomena continues to advance with new technology. Precise atomic clocks in orbit can now detect even subtle gravitational time dilation effects, while gravitational wave observatories provide direct evidence of how massive objects distort space-time. The implications of time-bending phenomena for space travel present both opportunities and challenges. While time dilation might theoretically allow humans to travel far into the cosmic future, it also creates fundamental barriers to maintaining communication and coordination across significant distances in space. The concept of proper time, the time experienced by an object on its own world line through space-time, becomes crucial in understanding these phenomena. Different observers can experience radically different proper times while traversing the same region of space, leading to the famous twin paradox and other counterintuitive effects. The relationship between time-bending effects and information preservation raises fundamental questions about the nature of reality. The apparent loss of information in black holes, combined with extreme time dilation, suggests that time itself might play a crucial role in how the universe maintains consistency and avoids paradoxes. As we continue to explore these phenomena, each new discovery reveals more about the complex relationship between gravity, time, and the fundamental structure of our universe. Time-bending effects remind us that our intuitive understanding of reality barely scratches the surface of what's possible in the cosmos. In our journey through cosmic horrors, we arrive at perhaps the most terrifying prospect of all, the ultimate fate of our universe. Unlike local catastrophes that affect single planets or galaxies, the final destiny of everything that exists unfolds on a scale that challenges human comprehension. The discovery of dark energy in 1998 fundamentally changed our understanding of cosmic destiny. Rather than slowing down under gravity's influence, the universe's expansion is accelerating. This acceleration points toward a possible fate called the Big Rip, a scenario where the very fabric of space-time tears itself apart. In the Big Rip scenario, the universe's expansion becomes so violent that it overcomes all fundamental forces. Roughly 22 billion years from now, galaxies would be torn apart. As the expansion intensifies, solar systems would be dismantled. In the final moments, atoms themselves would be ripped apart, reducing all existence to elementary particles scattered across an ever-expanding void. The heat death of the universe presents an equally disturbing possibility. In this scenario, the universe continues expanding eternally, slowly cooling until it reaches a state of maximum entropy. Stars burn out, black holes evaporate through Hawking radiation, and even atoms eventually decay. The universe becomes an infinite dark void where nothing meaningful can ever happen again. Quantum fluctuations in the final stages of either scenario add another layer of cosmic horror. As the universe approaches absolute zero temperature, quantum effects dominate. Random fluctuations might momentarily create short-lived particles, but these brief sparks of existence would only emphasize the eternal darkness surrounding them. The timeline toward universal death reveals a sequence of increasingly devastating events. First, star formation ceases as galaxies exhaust their gas supplies. Then existing stars die one by one, leaving behind a cosmic graveyard of white dwarfs, neutron stars, and black holes. Even these remnants eventually fade through various decay processes. The concept of proton decay suggests that matter itself has a finite lifetime. If protons can decay, as some theories predict, then all atomic matter will eventually dissolve into radiation, regardless of other cosmic events. The timescale for this process exceeds 10 to the power of 34 years. But in an eternal universe, even this becomes inevitable. The fate of black holes presents another aspect of universal death. Through Hawking radiation, black holes slowly evaporate, releasing their mass energy back into space. The largest black holes would take roughly 10 to the power of 100 years to evaporate completely, marking one of the last major events in cosmic history. As we contemplate these cosmic endings, we're forced to confront the transient nature of existence itself. Everything we know, every star, planet, and form of life, represents a brief moment in an unimaginably long cosmic story. Yet this very transiency might make the present moment more precious, not less. Throughout our journey across the cosmos, we've encountered phenomena that challenge our understanding of reality itself. From the mysterious depths of cosmic voids to the reality-bending power of black holes, From the destructive force of gamma-ray bursts to the unsettling possibility of vacuum decay, the universe reveals itself to be far stranger and more terrifying than we ever imagined. These cosmic anomalies remind us of our place in the vast cosmic arena, a species capable of comprehending the very forces that could spell our doom. In this understanding lies hope. Each discovery, each new piece of knowledge brings us closer to unlocking the fundamental mysteries of existence. If you found this journey through space's most terrifying phenomena fascinating, don't forget to like and subscribe to Space Mysteries. Your support helps us continue exploring and sharing the universe's deepest and darkest secrets. As we look toward the future, both of our species and of the cosmos itself, we're reminded that every end is also a beginning. Even in a universe destined for eternal darkness, the light of human curiosity and understanding shines bright, illuminating the shadows of space and time, revealing the awesome and terrifying beauty of our cosmic home.